Hello, I just finished explaining the general approach to solving a projectile motion problem, so now I'm going to go through and we're going to do an example problem. Okay, let's go up. I want to leave some of these things. Let's see. I want to take out all this crap. Take out this. Take out that. We can get rid of this Venn diagram. I want to leave this, though. Let's leave this in that bottom corner over there. Okay, so let's say that I throw a ball. I'm going to throw it at, let's say, 5 meters per second. Not very hard, but good enough for the example. And I'm going to throw it at an angle of 20 degrees. Right? And they're going to ask, how long will it stay in the air? Okay, well, let's list what we know in the x direction, and that's in units I, right? I with that stupid little triangle above it, so you can just write I. No one's going to care about the triangle. And then we're going to write what we know in the j direction. I mean, in the j units, which is the y direction. So here, we know that the initial velocity, actually, yeah, okay. So the initial velocity is equal to the final velocity, right? Because it's not accelerating. We know that much. What's that going to be equal to? Well, it's going to be equal to kind of like this shadow. So that's going to be the 5, the hypotenuse, the radius of the circle, times this this kind of shadow, the x piece. So we end up with, if you remember, that's going to be 5 times the cosine of 20 degrees. And that is equal to, handy dandy calculator, I'm going to type in 20, take the cosine of that, 20, take the cosine of that, and then multiply that times 5, there's our final answer, I'm going to put 698. 4.698. Keep some decimals there. So now we have 4.698 as our initial and final velocity. I'm going to clear that just to keep room. There's two pieces of data. Acceleration equals 0, right? So we know that much. Here, in the y direction, what do we know? Well, first off, right away we can say that, just like this, the initial velocity, we don't know the final velocity because there is acceleration in the y direction. But the initial velocity is going to be equal to 5 times the sine of 20 degrees. Hopefully you're getting more familiar with seeing the sine and cosine. Hopefully I've given you enough examples. So we're going to type in 20, take the sine of that, and then multiply that by 5, and we get this number 1.710. So that equals 1.710, or I'm just going to erase that to save space. We know that the acceleration in the y direction is going to be equal to 9.8, or rather negative 9.8, and that's meters per second squared, of course, or meters per second per second. I'm going to say it like that. And what else do we know? Well, we know that if it's going up and coming back down, that means that what's the change in the height of the ball or whatever? Well, that y, that delta y, the change in y, is 0 because it's going up and it's coming back down. They're going to be at the same height in the end. So, okay, which side do we have at least 3 variables known on? Well, we know both of them. But which one can we use to find how long it's in the air for? Well, that's going to be the y. And this is where actually this equation right here becomes really, no, I lied. This equation right here becomes really useful. Am I doing this in a more difficult way than I need to do? Because I feel like I might be. I don't want to show you a more complex way than I have to, that's for sure. Okay. So if we just plug things in, remember this is delta x, that's change, that's displacement. So we've got 0 is equal, that's the height. The height is going, which is 0 in our case, is going to be equal to the initial velocity, which is 1.710, we figured out, right? That's just this bit right here, this vertical bit, times whatever the time is, plus our 1/2 of a. Well, our acceleration is negative 9.8, right? So we got negative 9.8, and then since it's 1/2, we'll just divide that by 2. And then it's that times t squared, right? Oops. And I'm not making this up, this is just what we figured out in our equation right here. So that's half of the acceleration times t squared. That's just what this says. And then this is the initial velocity times time. Now I might say, ew, it's a quadratic equation. Factoring. Nope. No factoring. Well, kind of factoring. Simple factoring. What happens if you divide the entire equation by t? Oh, look. You get 0 over t. Well, what's 0 over... Oops. 0 over t. What's 0 over t? Take a guess. It's 0. So 0 equals 1.710. Well, the t disappeared, right? Because we divided by t. So then minus 9.8 divided by 2, that happens to be 4.9. I'm just taking the negative here and turning it into a minus sign. Minus 4.9. What's t squared divided by t? T squared divided by t, well, that's t. Hopefully that makes sense. If not, review your algebra. And then we could add this 4.9t to both sides. We get 4.9t is equal to 1.710, right? And then we just divide. We solve for t. We get t equals, we divide by this 4.9, and we get 1.710, we'll put in, divided by 4.9 equals, and we have 0.349. 0.349. So that's how long the ball stays in the air, right? So what can we use that to determine? Well, this value right here we can include in our calculations in the x direction. So I'm going to add that to our list of what we know. Now they almost always ask you how far is it going to go. And the answer to that is just going to be, well, distance equals velocity times time. There's really no simpler way of putting it. The distance that you travel is equal to the speed that you're traveling at, which is this right here, which is equal to that right there. It's that times however long you're traveling at that speed for it, which is the time it's in the air, which is this right here. So it's this times this, right? That makes sense. The time times the speed gives you how far you travel. If you travel at 60 miles an hour for 2 hours, you go 120 miles. So, whoops, wrong window. Let's open our handy-dandy calculator. And we take that 4.698, multiply that by the 0.349, and we end up with 1.64 about. So 1.64. So that's how far it travels, 1.64 meters. Which, it kind of makes sense. I mean, we didn't throw it very hard. If that, I mean, hopefully the 5 meters per second kind of means something to you. We didn't throw it very hard. And we threw it at a kind of shallow angle, so it didn't stay in the air very long. And if it didn't stay in the air very long, well, then it's also not going to go very far. And this, quite clearly, isn't very far. Another type of problem that you'll see is they'll tell you, okay, it traveled this far, right? They'll say, okay, it traveled this far. What was the angle, maybe, they'll say. So then what you do is you've got how far it traveled. That means that you don't have the initial velocity in the x or y directions, right? Because you don't know what those components are. Except you can actually use this number and just one of these equations, and you can find out what each of these values are, or rather what this value is. And then by doing that, you know, because you know that it's the component in the x direction, you know that this 4.698 is going to be equal to the initial velocity in the x direction, which are the initial velocity in the x direction, which you know is just, well, whatever the initial magnitude was, which we know would say they tell us is 5, times the cosine of, well, whatever that mysterious angle was. So then you can say, okay, if you divide this by 5, so you take that clear 4.698 divided by 5. Hopefully that works. Yes. We get 0.993. We get about 0.940. So we get that equal to 0.940. And that equals cosine of t. So then you can just use that little function on your calculator. Inverse cosine of t, or rather of 9.4, or I mean 0.94. I'm sorry, 0.94, and that gives you t. Which basically what that's doing is that's saying, okay, if you have the cosine, and the cosine is, say, x, and this angle is t, well then the inverse cosine of x, that's hideously ugly, is going to be equal to t. So basically, you put in how much of it, or rather, I'm sorry, if this is the hypotenuse, this is the radius of the circle, that times the inverse cosine of t. So for argument's sake, let's say that this, oh my god, that's disgustingly ugly. Let's say that this hypotenuse is 1, and we know that this right here is x, that's the length. What inverse cosine basically does is it says, okay, if I know that this length is, say, 0.5, well then I can give you what this angle is. That's all inverse cosine does. So inverse cosine, if you know what the cosine is, but you don't know what the angle is, it solves that for you. Hopefully that explains some things. Hopefully now you'll know, maybe you'll remember how to tackle those two-dimensional projectile motion problems, because they will definitely be on the midterm. I guarantee it. 1, maybe 2, because that's just the kind of problems that they love to give. Especially the find the angle, or maybe find the initial velocity. Just use this approach. Write down what you know in the x direction, write down what you know in the y direction, and then whichever side you have 3 pieces of data for, in this case it was our y we started with, that's what you start solving for variables. You start off finding t, because remember that's the intersection of the two, that was the intersection of the two Venn diagrams, things, the circles or whatever. You always find t, and then you solve in the other dimension. Hopefully that helped. Next, I'm probably going to be going on to, I don't know, what was the next topic? I think it might actually be forces? Yeah, I might be going on to forces next. If not, you'll find out in the next video. I'll see you then.